Let's take a look at a situation where we've got a 30 Newton force applied to a 20 kilogram mass along a horizontal surface. There's no friction or anything. It's a pretty simple problem. And we want to know, okay, what is its horizontal displacement? What is the work done by that force? What's the change in kinetic energy? What's the change in velocity? So for part A, let me zoom in a little bit. Well, I want to know delta x, but what do I know? I know the initial velocity. I can find, because I know the force and the mass, I can figure out the acceleration. And I know the time, but I don't know the final velocity. I mean, I might have to find it later, but I don't. I'm not asked to find it, and I don't need it. So I'm going to use the third kinematic equation. When you don't need the final velocity, you use the third. So this is 0. Now we need to find the acceleration. Well, if I draw a little free body diagram of this guy, mg is down, normal force is up. We have this applied force, and this applied force is the net force. So Fa equals ma. So A equals that net force divided by m, which is 30 newtons, divided by the mass, which is 20 kilograms, 1.5 meters per second squared. I mean, I could put some of the forces in the x direction, but sometimes, I mean, look, I like to at least draw the free body diagram so I see all the forces acting, and I say, okay, that's my net force. There's only acceleration in the x direction, and it turns out to be 1.5. And then I get my calculator. 0.5 times 1.5 times 25 at 18.75. I'll call it 18.8 meters. You can put 18.75 if you want. Now we want to know the work done. Well, the work done by a force is equal to that force times its displacement times the cosine of the angle. So I look at what's the magnitude of the force. It's 30 newtons. What's the magnitude of the displacement? 18.8 or 0.75. And then what's the angle between them? And I always check this. You should get in the habit of always looking at the situation and checking the angle. Well, the force is to the right. The displacement is to the right. So the angle between them is 0 degrees. Of course, that's just 1. So you just take the displacement and multiply it by 30 newtons. So times 30. And that's, I round it off, it's 563. Oops, not newtons. Joules. Because a newton times a meter is a joule. And then part C. Well, part C is super easy if you know what, if you know the work energy theorem. The work done by the net force equals the change in kinetic energy. Well, this was the net force. So this was the work done by the net force. So the change in kinetic energy is 563 joules. No work needed. Well, you needed the work. Never mind. All right. Part D. What's the change in velocity? Well, the change in kinetic energy is equal to K initial minus, or k final minus k initial. 1/2 m. Well, v final squared minus 1/2 m v initial squared. Well, yeah, so we know that the initial velocity is 0, so we can solve for the final velocity. Equals 2 times delta k divided by the mass, take the square root. Basically, I took this equals this and solved for the final velocity. There's our values. So two times 563 divided by 20 equals, and then we're going to take the square root of that. And I got 7.5. Now, I didn't really ask for the final velocity. I asked for the change in velocity, which is v final minus v initial. So delta v is 7.5 meters per second. Let me zoom out and see the whole problem. Okay. Now what we're going to do today, later on today, is we're going to figure out another way of figuring out. You can use energy and work in energy to figure out the change in velocity of your object. You can also use kinematics. And today we're gonna learn a different method. But the exam will have something like this. Something like this problem. Any questions? That is all.